Welcome to breadboarding. In the previous video, we read the existing ROM from the original 1981 Nanocomp. We programmed a new, more up-to-date ROM, installed it and tested it. In this episode, we're going to install the RAM and the peripheral interface adapter and test that the PIA has the appropriate signals appearing on the port B and port A, so that when we hook up the LED display and the keypad, then we can be sure that things are working. If we look at our schematic, we installed the ROM last time. The RAM that we're installing here is much bigger than is required. It's actually a 1 megabit or 128 kilobyte RAM. So this means that it has 16 address lines, so A0 to A16, which is obviously way bigger than the address range of the 6809 microprocessor. We're only going to be using the bottom 4 kilobytes of RAM, and so what we're going to be doing, if you can see here, there's A16, A15, A14, A13 and A12 here. We zoom in to make it a little bit clearer. You can see that these upper address lines are just grounded, so that we'll only ever be using the bottom 11 address lines. And unlike the ROM, when we're only using 2K, we actually want to use all 4K of this, so we will be using the A11 line in this particular case. The PIA, as you may remember, the main thing we have to worry about this is the register select 1 and register select 0 are in fact connected to address 0 and address 1, so the reverse way. Most of the signals, so the chip select signals, will be held to high, and we use the Y4 signal from the address decoder over here to enable the PIA, which appears at the hexadecimal address 4000. A number of other pins, such as the CA1, CA2, CB1, CB2, we won't be using, and we're only using at the moment first 4 bits of port B, and we're using 7 bits of port A. And these then go off to the LED displays and the keypad. So what we're going to do is to first of all pick out the components, work out where we're going to put them on the board, and then we're going to hook them up. And then for testing this, we are going to check to see whether we get the expected signals on port A and port B. I'll be hooking up the logic analyzer just to check that we're getting the appropriate signals there. So here we've got the components we're going to be using here. So we have the 2 decoupling capacitors, the parallel interface adapter chip, which is a Motorola 6821 compatible device, and we've got the chip labels for that. And then we also have the RAM, 128 kilobyte RAM, for which we have the label for that as well. So what we're going to work out now is where we're going to place those on our board. And if you remember in the last video, what I've done is now mounted the breadboards on this chopping board or breadboard. This particular one is just from a supermarket. I think it cost about £6 and is actually not a bad size for this particular project. So we're going to need to add another breadboard here onto the end, where we're going to put the peripheral interface adapter, and we're going to be putting the RAM chip somewhere along the center here. It's in a similar configuration to the ROM chip, in that we've got 3 data lines on this side, the rest of the data lines on that side, most of the address lines on this side, and there will be A10, 11, A9 and A8 will need to come round the side here. So we probably need to allow a little bit of space for the data lines, and also some space for the address lines to come round as well. And thinking about how we want to line up, have we got BSS that can go to pins there? Can we fit Yes, we've got VCC there. So if we line that up with 55, then we should pretty much have most things. There are a lot of these pins are connected to ground, so we may end up connecting individual pins together rather than having lots of lines going up to the power rail there. And when we come to do the peripheral interface adapter, the main issue here is we need to make sure that we don't end up with data lines coinciding with the data lines here, because we may run into issues with these not working quite right. So what we'll probably want to do with this particular chip is to perhaps have the data line. So D0 is at the top here. So, and D7, which is down here. So in fact, we can overlay these reasonably. D0 is going to come down to here, and D7 is going to come down to here. So in fact, this will actually work out quite nicely. So we're going to need to put that so that the D0 is slightly above the D0 here. And we're also going to need to feed the address 0 and address 1 lines from here up to here. So in fact, we can do that. So probably fitting the chip just about there will make the wiring up things easier. So I have another new breadboard here. So I'm just going to hook this up to the top of this, and we just need to slot this over. Here we go. And I think we're going to want to make sure this will be lined up on 35. I think if that's lined up on 35, then yes, it will. So this one's going to be lined up on 35, and this one's going to be lined up on 55. So we're going to first of all put the labels on the chips. So this is the 6821, which is a peripheral interface adapter, standard Motorola chip. This may not necessarily be a Motorola one, it's probably a compatible one. And then we'll make sure we try and line up the pins as well as possible. Make sure pin 1 is at the top, yeah. And as much as possible, try and line the pins up as well as possible. Right, so that's that one. Then we've got the RAM chip, pin 1 at the top there. And try and line this up. Yeah. Reasonably lined up. Okay. So whilst I can still remember where we were going to put these, I think this one was going to go in at 55. Again, we probably want more holes on the top side than on the lower side. And then this one was going to go in 35. You actually want to have it with the data bus on this side. So if this is on 35, let's just check that D0 is still going to be lined up. D0 is going to be coming to there. So that should be fine. So for the moment, I'm just going to disconnect the logic analyzer from there for the moment. You hook up the power first. The VSS is ground. And VCC is 5 volts. And now with this board, we can't quite easily see the schematic. So what I'm going to do is just bring that up. So if we look at the schematic here, we can see that apart from right enable here, pins at the top here are largely taken to ground. The pins 2, 3 and 4 here are also taken to ground. Then we just got the address lines, the data lines, and then the chip select as well. Output enable, we're going to tie to ground as well. The majority of these pins are going to be tied to ground unless they're the address or data lines that we want, and the chip select is going to go to Y1, so it's fairly straight. What I have just noticed is that the chip select, inverted chip select, so when this is low, the chip is enabled. CS2 is actually enabled when high. But at the moment we've got this tied to ground, so I think the join here has perhaps confused things a little. So we expect A15, A13 to be tied to ground, but chip select 2 needs to be tied to 5 volts. So I should make a correction for that, and we'll just check it on the data sheet. This is the data sheet for the RAM, and you can see here that CE2 has to be high for the output to be available, and the chip enable will always be low. Output enable we're going to tie low because we don't want to make use of that, and the write enable is read write. So it looks like I did make a mistake there. So CE2 needs to be tied to plus 5 volts. We'll make a correction to the diagram for that. So that's now start to plug in various data lines and address lines. So let's just let's do the chip enable first, so we don't forget that one. The chip enable 2 is going to be tied to plus 5 volts. Address 15 is going to be tied to the ground because we don't want to make use of top 5 bits. And then A13 is also going to be tied to ground. And we're going to be using A11, A10. Output enable we want to be tied to ground. Always. Chip enable is going to go to chip enable is going to go to the Y1 output over here, and then we also need to do these address lines here as well. So A16 can be tied to ground. A14 also. I got these larger RAM chips just because I thought, what's the point in getting a small chip when you can have a larger one? When we come to look at perhaps doing larger processors like the 68000 series or 8086 series, then we'll certainly need that extra RAM. Okay, so I think we've done all the address lines are now tied to ground. Chip enable's tied to plus 5, so we need to wire up the read-write signal, chip enable signal, and then all the address lines. Everything else hopefully should be sorted. So first we're going to do chip enable. So this is going to go from in Y1 there, going to go to chip enable over here, or go underneath those wires, chip enable, and then we need to do on 2.5 after that. Now, that. Okay, then we're just going to feed that underneath those data lines. Most of it, I normally put the control lines in first and then put in the data lines afterwards, but in this particular case, because we've done the ROM first. So we go, and we'll then open that. Not quite the right length there, but it will do for now. Could do with we just tightening that slightly. Okay, so that's chip enable. We're also now going to do the read write. So read write is this line up here. So write enable is going to go to read write. So just going to plug that in here. So read write, then we're going to add another one to a little bit less this time, so we get tighter. Okay. A little bit tighter that one. So that is read write, and to write enable. Got chip enable. Now we're also going to need to do the white wires for all these other ones. So for all the address lines and the data lines, I'm just going to speed this up. Let's just check off all the pins. So we've got plus 5 volts. Then we've got, this is the correction. So these will all be ground, and this one is plus 5. So we've got A15 is ground. Chip enable 2 is plus 5 volts. Write enable is going to read write. A13 is going to ground. A8 is going all the way around to A8. A9 going all the way around to A9. A11 is over here, comes down to A11. Output enable is going to ground, so it's always enabled. A10 going around to A10. Chip select, chip enable is going to Y1. Into Y1, yep. D7 into 7, D6 to 6, 5, 4, 3, 2, 1, and 0. So 3 is going, sorry, D2 is going to here, D1 going to there. Yes, so those are all good. Ground, yep. Then the address lines A0 is going to A0, A1, A2, A3 going to A3, A4 goes to A4, A5 to A5, A6 to A6, A7 to A7. Then we have 12, 14 and 16 all tied to ground. 12, 14, 16 all tied to ground. The only issue we have to do here is to make the change to plus 5 volts for chip enable 2. That's all done there. So the next thing we're going to do is to wire in the PIA. So now we're going to hook up the peripheral interface adapter. So we decided to put this end on 35. So we're going to go through and put on the power first. So this is VSS, which is ground. This is VCC. We have the right pin. VCC, VSS. We're going to leave most of the pins on top there because we don't need to do very much with those. So we're now going to hook up the various chip selects. So chip select 0 is going to just check these off. Chip select 0 is going to go to 5 volts. So we need a short 5 volts here. Chip select 2 is actually going to go to Y4 down the bottom here. Chip select 1 is also going to go to 5 volts. Let's just do this. Now we've also got read, write and E signals, which are going to go to the here. So let's hook these up a moment. So just hook this up. Read, write. Going to read, write is here, and we want to go about another 2.5. Okay. read write, goes into the right. Slightly too long, but will do for now. I want to do the E signal. Slightly longer. Now E. Up a little later. Oops, sorry. E. D. E is going to E. Read write is going to read write. So chip select there needs to go to 4. I think what we'll do for this one, need a slightly longer bit of blue wire. This one we probably want to go close to the chip. And then we can bend all the way down to and to Y4. I'll just bend that back in place. Right, so we now have done read write. Up to read write. Chip select 0 connected to +5. Chip select 1 is also connected to +5. Chip select 2 connected to Y4. Is connected to Y4. E is connected to E. Then we just have to worry about D0 to D7. The interrupts we're going to up to IRQ. And then the main thing we have to worry about is RS0 and RS1 going to A1 and A0. So the reverse way around plus reset. Let's just do reset. So reset is going to be this lower one here, the other one's for the button. reset. Now RS0 needs to go all the way around to A1, and RS1 needs to go down to A0. We need some long green wires for this one. It's the only bit we've got left, so let's cut some more green. So we're probably going to route this underneath, so RS0 going to go underneath here down to A1. And then RS1 is going to go to A0. A0. We're probably going to get this to go underneath some of these other ones. RS1 goes to A0. Just put it underneath. Yeah. And RS0 goes to A1. And this goes to zero. Trust me on this one. These two wires now go down to A1 goes to RS0 and RS1 goes to A0. So if we just check this off on our diagram, RS1, A0, A1 to RS0 and reset. Then the interrupt requests, we can tie those two together and tie it to IRQ. So I might just do a small let's just do those from each of the IRQ lines. It's probably easier rather than tie them together. So the IQ, well, the non-maskable interrupt is there, so we need to buy do the other one. also wants to be the same width. Just tying the interrupt lines up to IRQ, should we want to use them at some point. I need to. Just take this out to make this slightly shorter. Shorter, but not quite short enough. Right, there we go. We're going to have IRQ and there. So we only have the D0 to D7 lines to do. I'll do that speeded up without any commentary. So now we've installed the logic analyzer on the PIA port B and port A outputs, and I've also hooked up my older logic analyzer, the LA1010, to the address line so we can actually see what the address lines are doing. But one of the things we do need to do before we power everything up is we haven't put any power lines into this new breadboard. So we're just going to put the two rails together. So that's ground hooked in together. Let's just now turn the 5 volts. And I'm just going to wire up the power rail from our processor in here. And in my breadboarding tips video, we talk about distributing power, not chaining power between too many boards, but this should be fine in this particular case. And one of the tips in that video is to use this small voltage meter, which is a neat little voltage meter that you can put on the power rails at the remote parts of your project, and will show you if you have any problems with your power. So we now have the power hooked up. So what we need to look at first of all, before we go any further, is what are we expecting to see on these analyzers. So here are some screen captures from the original January article, which showed where the 7-segment displays were mapped to the individual bits in the display codes. And then this is from the July issue for the 6809 version of the design, and it shows where the port B 0 to 3 outputs go to the decoder and which values will be mapped to which values in the display. So the 7-segment display is values 4 through to 9. So when PB has got a value of 4 to 9, then it will be addressing the 7-segment display. 0 to 3 is scanning the keyboard. And on the 6809, the 6 digits are displayed from memory stored at 13FA for the left-hand digit and 13FF. Now the monitor shows a minus sign on the left-hand side of the display when waiting for input. So we'd expect that when PB is 04, we would see the code for the minus sign to be displayed here. Now the code for the minus is 01 hex, so that means that only this segment is illuminated, and that's the lowest bit, which is 0 or 1. So when that's 1, then that will be illuminated. However, because of the way how the electronics work, when we receive a 1 on the port A, what it in fact does is uses a dialing transistor to pull this from 5 volts down to 0 volts. So in fact, it turns the display off, as we discussed in earlier videos. So in fact, what we're looking for to have a dash or a minus sign here is either a value of FE or 7E, depending on if we're looking at the most significant PB7 output. Nanocomp doesn't use PB7, so we could probably ignore it. So expect FE or 7E when port B is outputting the 04 if the monitor is displaying the prompts like this. So we're just going to start up the logic analyzers before we turn on the power. I'm just going to run up the, I'm just going to plug in the LA1010 first, so you don't get confused. So this is the LA1010. You can see we've got A0 to A14, and we need to just trigger this on the bus status going from high to low, which occurs after reset. Now the analyzers, the label here, there seems to be a bug in the software, in that although we've got this set at A0 down to A14, it does take the label from the other one. So let me just put this as A14. I will just save this just to make sure. This is A0 to A14 with bus status. So that has saved that analyzer. Now we're going to run up another copy of Kingst, and for this we're going to attach the LA2016. So I'm just going to plug in now the LA2016. Now be detected. So we've got the LA2016, we just need to load the right configuration. So have these saved previously, PA 0 to 7 and PB 0 to 3. You can see we've got PA 0 down to PA 7, PB 0 to PB 3, and also status. And the analyzers here will just check the PA 0 to PA 7. Yep, that looks correct. PB 0 to PB 3. That should only have those 4 lines being looked at. So we only want to have the 8, 9, and 10 lines, which these ones 8 and 10. Right. And all I'm going to do here is just show the PB values really first. So we're now just going to start these analyzers. They're looking for the high to low value on the bus status, which occurs after reset. We're just going to set that one to be running. Then we'll set this one to be running. Just going to run that. So we're now waiting for the trigger, and what we'd expect now when we plug in the power is that we should see the bus showing 7FFF to start with, and then loading the reset vector, and then starting to access the ROM and the RAM as it starts to run. It looks like we've got what we expect here. If I just zoom in on the period after the reset and see the bus status changes. We have 7FFE, which is the first byte of the reset vector, 7FFF. Then we're looking at 7D89, which is the reset vector as we talked about previously. Then we can see that the processor is going through reading memory, more memory, and at some point in time, it'll actually start to look at the memory. So we're looking for 13FA. Now 13FA, we should see somewhere down here where the code starts to access 13FA. There we go. So in fact, this is where 13FA is read, and you'll probably see that there will be 13FB as well. So it looks like it's got to reading the memory where the 7-segment display information is stored. So let's now go back to our other instance of Kingst. We can see here that after the reset, we zoom in. After the reset, we get some values going out on port B. You can see we've got 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, and then it goes to A, B, C, D. But what we're interested in here is when it's 0, 4, what is the value which is being output? And we can see here, in fact, that we enable the other set of decoded results. We can see that, in fact, when PB is 0, 4, that we're actually getting FE output here. If we change this analyzer to only include, we change this analyzer to exclude PB7, then in fact we'd see it as 7F, 7E. So 7F will mean none of the segments are displayed. 7E means that only the middle bar will be displayed. So that's what we expect. So hopefully this means that the monitor is running and it seems to be outputting a minus sign to the left-hand segment. So when we wire up the LED display and then we attach the keyboard as well, we would hope that this is working okay. So that's good news. And what I'm going to do in the next video is we'll look at building the circuit with the 7-segment display and the Darlington driver and the decoder, so that we can at least hook that up and start to see if we can get any values on the display. And then the video after that, we're going to build the keypad on some strip board, and that involves soldering. So that'll be in the video after that. So if you don't want to miss out on anything, please hit subscribe, and thanks for listening and watching.